We now define the conjugate of a complex number. Let z equal to a plus iota b, where a and b are real numbers. Then z bar equal to a minus iota b is called the conjugate of z. It is denoted by z bar. A becomes the real part of z bar and minus b becomes the imaginary part of z bar. Following results can be easily established from the definition of a conjugate of a complex number. First is z bar double bar is equal to z. Z is equal to z bar if and only if imaginary part of z is equal to 0, that is, z is purely real. Third, z is equal to minus z bar if and only if real part of z is equal to 0, that is, z is purely imaginary. Fourth, z plus z bar is equal to twice real part of z, and z minus z bar is equal to twice imaginary part of z. Fifth, z1 plus z2 whole bar is equal to z1 bar plus z2 bar. Sixth, z1 minus z2 whole bar is equal to z1 bar minus z2 bar. Sixth, minus z whole bar is equal to minus times z bar. Next, z1 into z2 whole bar is equal to z1 bar into z2 bar, which can result into zn, z raised to power n whole bar is equal to z bar whole raised to power n, and z1 upon z2 whole bar is equal to z1 bar upon z2 bar. If z is a function of z1, then z bar becomes the function of z1 bar. All these results can be very easily established from the definition of the conjugate of a complex number. The next and most important concept of a complex number is the modulus of a complex number. If z is equal to a plus iota b, then the modulus of z as mod z is defined as mod z is equal to square root of a square plus b square. Following properties follow immediately from the definition of the modulus of a complex number. First, mod z is greater or equal to 0 and is equal to 0 if and only if z is equal to 0. That means real part is 0, imaginary part is 0. Second, mod z is equal to mod z bar is equal to mod of minus z is equal to mod of minus z bar. Third, z into z bar is equal to modulus of z square. Fourth, real part of z always lies between minus modulus of z and plus modulus of z. Similarly, imaginary part of z also lies between minus modulus of z and plus modulus of z. Next result is modulus of z1 into z2 is equal to modulus of z1 into modulus of z2, which implies modulus of z raised to power n is equal to modulus of z whole raised to power n. Also, modulus of z1 by z2 is equal to modulus of z1 divided by modulus of z2. Next, modulus of z1 plus z2 is less than or equal to modulus of z1 plus modulus of z2. This is also called triangular inequality. Next, modulus of z1 minus z2 is greater or equal to modulus of z1 minus modulus of z2. Also, modulus of z1 plus z2 whole square plus modulus of z1 minus z2 whole square is equal to twice modulus of z whole square plus modulus of z2 whole square. Modulus of z1 plus z2 whole square is equal to modulus of z1 whole square plus modulus of z2 whole square plus twice real part of z1 into z2 bar, and modulus of z1 minus z2 whole square is equal to modulus of z1 whole square plus modulus of z2 whole square minus twice real part of z1 into z2 bar.